Deep within the heart of every proton, neutron, and atomic nucleus lies a force that is invisible yet unbreakable, a force carried by particles known as gluons. These particles are the messengers of the strong nuclear force, the invisible threads that tie quarks together, giving rise to the protons and neutrons that form the building blocks of matter. Gluons are massless, yet they carry a property called color charge, which allows them to bind quarks in a dynamic and unending dance of energy and motion. Without gluons, quarks would drift apart, atoms would disintegrate, and the universe would be a formless, structureless void. Gluons operate in a realm that defies intuition. Unlike photons, which mediate the electromagnetic force without interacting with each other, gluons can interact with other gluons as well as with quarks. This self-interaction creates a complex, vibrant, and highly dynamic environment inside nucleons, where energy fluctuates constantly and quarks move in patterns that are both constrained and unpredictable. These interactions are described by quantum chromodynamics, a theory that reveals how the color charges of quarks and gluons combine to produce the particles that form matter. Each proton contains 3 quarks and a swarm of gluons, yet the interactions among them are so intense that they dominate the mass and energy of the particle, far exceeding the combined mass of the quarks themselves. The behavior of gluons explains confinement, one of the most fascinating aspects of quantum physics. Quarks cannot exist in isolation because the strong force, mediated by gluons, becomes stronger as they are pulled apart. This property ensures that quarks are permanently bound into composite particles, forming protons, neutrons, and mesons. If we attempt to separate quarks, the energy input simply produces new quark-antiquark pairs, maintaining the integrity of the nucleon. In this way, gluons act as the ultimate glue, an invisible network that ensures the stability and cohesion of matter. Gluons also play a critical role in the behavior of exotic particles and high-energy states. In particle accelerators, collisions can generate short-lived states in which gluons dominate the interactions, producing mesons, baryons, and even exotic gluon-rich states called glueballs. These phenomena allow physicists to probe the nature of the strong force in unprecedented ways, testing predictions of quantum chromodynamics and exploring the limits of our understanding. Through these experiments, gluons reveal the deep structure of matter and the intricate rules that govern its behavior. Beyond their role in individual particles, gluons influence the processes that power stars and shape the cosmos. Nuclear fusion, the process that powers the Sun and other stars, depends on the interactions of protons and neutrons, which are themselves bound by gluons. Without the energy mediated by gluons within nucleons, the fusion reactions that sustain stars could not occur, and the universe would lack the light and heat essential for life. The gluons within every atom thus connect the microscopic quantum world to the grand scale of cosmic energy, bridging scales from the tiniest particles to the most massive stars. Gluons challenge our perception of reality because they exist only within the quantum field. They are not free-floating particles in the way photons or electrons can be, but they are essential carriers of the strong force, shaping the structure, stability, and interactions of matter. Their influence extends to every atom, every molecule, and every process that relies on the integrity of matter. They are both invisible and indispensable, subtle yet overwhelmingly powerful, orchestrating the forces that give the universe its form and substance. In extreme conditions, such as the early universe moments after the Big Bang, gluons existed in a free state within the quark-gluon plasma, a hot, dense soup where quarks and gluons moved independently before cooling and binding into protons and neutrons. Studying this primordial state allows scientists to understand the origins of matter, the formation of nuclei, and the emergence of the universe's structure. Gluons, in their fleeting freedom, reveal the energy, chaos, and order that underlie reality itself. Contemplating gluons is to contemplate the hidden scaffolding of matter. They demonstrate that stability arises not from the quarks alone but from the dynamic interplay of forces mediated by invisible threads. They remind us that even the tiniest scales of reality are alive with interaction, fluctuation, and energy, and that the universe's complexity emerges from these subtle and powerful connections. In essence, gluons are the invisible architects of the quantum world. They bind, sustain, and shape matter at its most fundamental level, ensuring the cohesion of particles, the stability of nuclei, and the processes that fuel stars and galaxies. By studying gluons, we gain insight into the hidden dynamics that underlie reality, revealing a universe woven from forces, energy, and interactions that are as invisible as they are indispensable, as subtle as they are powerful.